Okay, so in this question here, we are asked to prove from first principles the derivative of a function. Remember, the derivative of a function is its reaction at a point. So how steep is it at a certain point, its gradient at a point. And in order to do that, we look at small changes. I do go over this in another video, so this is just an outline here. But what we are looking for is when we have 2 points, for example, P and Q here, and we've got the X and the Y coordinate for each. This Q has been increased by a very small distance of H. So our X coordinate for P is X and for Q is X plus H. And our Y coordinate is f of X. So substituting that value of X into whatever function this is, and we get the Y value. And for Q, we're going to substitute X plus H. And we look at the gradient. So remember, the gradient is the difference in Y divided by the difference in X. And when this value here gets smaller and smaller, Q approaches P, so H gets much, much smaller, we end up with a function. So what I mean by that is, if we were to look at the gradient here, so difference in Y, which is f of X plus H, this Y, minus the difference, or minus Y here, which is the difference in, which is the Y coordinate for P, divided by this H that we've increased it by. So if this is X and this is X plus H, then my difference here is H. So X plus H minus X, you could say, which is the same as f of X plus H minus f of X divided by X minus X is 0, so divided by H. And what we say here is we're going to make this H get smaller and smaller. And the notation that we use here is that this differential here, this dy by dx, we can represent as f dash of x. So that's the same as dy by dx, the differential, first order differential here, or the gradient function is sometimes called. We can represent this with the notation that what we're going to do is we're going to make H approach 0. So when we make H approach 0 in here, then we make Q get much, much, much closer to P, and eventually we get this, what we call the tangent here, and we get the gradient of this line here. We get it at P. Now, there's an important point to notice here. H doesn't equal 0. H gets very, very close to 0. So, as I say, if that's that concept there is slightly confusing to you, please do look at my other video on this. So this is first principles, and if we were answering a question like this in the exam, we don't need to go through all of this explanation here. We can just quote this here. This equation here we can just quote, so we can write this down first. We're asked to show from first principles that when the function is y equals 2x cubed, so f of x, which is y, remember, equals 2x cubed, then f dash of x, so dy by dx, so we're going to look at the reaction of this function. What does that equal? We're going to try and show that it equals 6x squared. So what we do is we look at this here, and as I say, we write this down first, and then we just substitute in our function. So we would first of all say f dash of x would equal the limit when h tends to 0. So we are going to make h much, or very close to 0. First of all, fx plus h. So we will put up, this would be 2 into x plus h cubed minus f of x, which is 2x cubed, divided by h, and we would multiply this out. So let's do that. So our first step here, let's multiply out this. So the limit of h tends to 0. Let's multiply out this bit here. 2 into x plus h multiplied by x plus h multiplied by x plus h minus 2x cubed all divided by h. Okay. So just for completeness, I'm going to keep this going here. So the limit of as h tends to 0, that's how we say it. So h tends to 0, and I'm going to multiply out these brackets and multiply them by 2. So let's go 2 into, well, this would be these two brackets multiplied together will give us 2hx plus h squared, and x squared at the start, and I need to multiply that by x plus h, and that equals, notice that I'm taking my time to multiply out each term. I don't want to make a mistake here, and there's a check, an inbuilt check that we're going to see in a second. So just simplifying inside that bracket, we get x cubed. These terms here go together, so we have plus 3h x squared, and these two terms here to go together, we get 3h squared x plus h cubed. And did you spot the inbuilt check here? The work on Pascal's triangle and the binomial theorem would say that our coefficients here should be 1, 3, 3, 1, and we have that. So continuing, now here we can cancel out. We've got 2x cubed, take away 2x cubed, and so our limit as h tends to 0 of 6hx squared plus 6h squared x plus 2h cubed all over h. H divides into each of these terms, as you can see, and we get the limit h tends to 0, and you'll see now the relevance of this limit. 6x squared plus 6hx plus 2h squared. Now, if h tends to 0, so remember it gets so close to 0, that would mean that this term here would disappear, because anything multiplied by 0 is 0, and here anything multiplied by 0 is 0. It's important again to say that this is a paradox in some ways, that h doesn't actually equal 0, but it does equal 0. In my other video, I draw the analogy, if you remember, that a third is 0.3 recurring, 2/3 is 0.6 recurring, so 3/3 would be these added together, 0.9 recurring, but 3/3 is equal to 1, as we know. So 0.9 recurring is equal to 1, or is it? So it's that kind of thinking that relates us to this idea here. So in other words, f dash of x, so dy by dx in this case, to our function differentiated is, as I say, these two terms here disappear because as h tends to 0, which is the point of differentiating, h tends to 0, we end up with 6x squared. And that was what we were asked way back at the beginning here, to show that dy by dx equals 6x squared.